In the 2020s, we are surrounded by light-emitting diodes. They are the lights in this room. They're on almost all of our devices. And what's interesting about them is that we can use them to get some ideas of what's going on at the single electron, single photon level as they convert electrical energy into light energy. How LEDs and semiconductors work is beyond the scope of this course. But we have looked at the Bohr model of the hydrogen atom, and we know that promoting electrons to higher energy levels requires energy, and when they fall back down, they emit light. And that's kind of a key feature of how LEDs behave as well. For electricity to travel through an LED, electrons have to be raised in energy to higher levels, and then later on in the process, when they fall back down, they emit light. So the electrons that are given enough energy to get to that higher state and start moving, we can represent that as electric potential energy, which we know is equal to Q delta V. In other words, we apply a voltage difference across the LED, and that's going to let charges start to move. When those electrons fall back down, they're going to therefore emit photons. And the photon is going to correspond to how much energy we gave the electron to cross the band gap, in other words, to get to the higher energy level. So I have this demonstrator with LEDs of different frequencies, and I have a generator that as we spin it faster and faster, the voltage increases. And this is going to show us that we need higher voltages for higher frequencies. This demonstrator here was put together by Arbor Scientific, and it's got some LEDs of different colors. On the far right is an infrared one, which I can't see, but you'll be able to see a little bit through this iPad camera. Then comes red, then comes green, then comes blue. We know red has the lowest frequency, blue has a higher frequency. The energy per charge needed to light up red is less than the energy per charge needed to light up blue. So I have this all hooked up to one of those hand crank generators. I don't think you can, oh, there we go. It's the kind we had when we were talking about electricity and magnetism. And as I spin it, you'll hear it go faster and faster. So I'm going to start out really slowly. And you can see we get flashes in the IR one and flashes in the red one. The thing's not putting out much voltage, not much energy per charge when I spin slowly. But if I increase it, I'll have more voltage, more energy per charge. And we should see green start to light up. There we go. But notice I have to go faster to make that happen. And if I start going really fast, a lot of energy per charge, we start having blue light up. So here's our experimental setup. We've got a variable power supply. We have a series circuit with a current limiting resistor, our LED, and we can take the potential difference across the LED with a multimeter, and then it goes back to the power supply. LEDs have a polarity. The flat side of the LED is usually the negative side. We're going to vary the LED from 622.5 nanometers wavelength on the red one to 452.5 nanometers on the blue one. And we're going to look at the different turn-on voltages for each. We're just going to dial up the potential difference until we see the LED come on. And there it is. That's brighter than we want, so we're going to dial it down until we can barely see it. And then we can even check in the dark if we want to. Looks like I have to dial it down a little bit more. Because we want our estimate of the band gap energy to be as precise as possible, it is really important that the LED is very dim, that we're counting just when it barely turns on. So this is a nice example of what you're looking for. And then I'll take the potential difference across it. And there it is. And now we're going to repeat for all the other different colors. So I've listed all my LEDs by color and wavelength, but I've gone ahead and converted that wavelength into frequency. because it shows us that as frequency increases, so does the voltage required to turn the LED on. Getting back to our statement of conservation of energy, the energy we have to supply electrons to enter the excited state is equal to Q delta V, and then later when they fall back down, the photon they emit is HF. I divide both sides by the charge on an electron, and I get delta V equals H over Q times frequency. Lining that up with our linear equation, we can see that a graph of turn-on voltage on the y-axis and frequency on the x-axis should be linear with a slope of H over Q. So of course we can make that graph, and we do get what we would expect. A linear graph with a slope of 4.5 times 10 to the negative 15th. So when we set that equal to H over Q, we get an estimate of Planck's constant of 7.2 times 10 to the negative 34th joule seconds. That's 8% error. I did this lab pretty quickly by myself. I wasn't able to turn all the lights in the room off. We've gotten closer when we've done the lab in class. So I hope this was a decent overview of an elegant way of measuring a fundamental constant in nature, and I hope you feel like you learned something from it.